Thank you, Lydéric, for the kind introduction and for the invitation. I'm really excited to be here in this workshop. I can see lots of different techniques at looking at interfacial water. And I can see as well a lot of interest in understanding the correlation between the electronic degrees of freedom in the system and the ionic degrees ones. So very, very exciting seminar. So today I would like to talk to you about our work investigating interfacial water dissociation through proton permeable electrodes. So you may be aware that there's a large group of materials like graphite, hexagonal boron nitride, and these materials consist of atomically thin layers that are stacked on top of each other. Now, crucially, the bonding between these layers is very weak, so it's possible to mechanically peel one of these layers to form a two-dimensional crystal. Now, one of the key properties we're interested in of these crystals today is that these crystals are impermeable to all atoms at ambient conditions. Not even helium, the smallest, can permeate. And this has been proven by a now series of seminal experiments by Bunch et al. And also Andre Geim. And basically, the experiment, what they do is they drill a micron-scale cavity in a substrate. This could be silicon oxide or graphite. And then they seal this cavity with a 2D crystal. This could be graphene, HPN, or whatever. And then they pressurize this cavity with pressurized gas. And what happens is your 2D membrane bulges upwards pretty much like a balloon. And this deflection can be monitored using an atomic force microscope. And by monitoring this deflection, you can tell what's the pressure inside the cavity. And in these experiments, they demonstrated that these crystals are impermeable to all atoms. The second property we're interested in today is that these crystals are permeable to protons. So back in 2014, we showed that in the outer plane direction, these crystals are permeable to protons. And what we did is we did membranes like the ones for nanoballoon experiments, except we sandwiched them with 2 layers of proton-conducting polymers and proton-injecting electrodes. So when you apply a bias, what you basically do is you drive protons through your device, and by measuring the resistance of this device, you measure the proton conductivity of the crystal. And what we normally see is something like this. This is current versus voltage for monolayer hexagonal boron nitride and monolayer graphene. And what you see is that monolayer boron nitride is much more permeable to protons than graphene. Now, if you compare this to MOS2, you see that graphene is still pretty permeable. And for MOS2, even though it's a single layer, we didn't see any proton conductivity at all. We repeated these experiments. Each of these bars is a different device. This is statistics of proton conductivity for the different crystals we tried. And if you look at this, you see that, each bar is a different device. And if you look at, say, monolayer boron nitride, compared with bilayer and trilayer, you see that for each layer, the current drops by about an order of magnitude. For monolayer graphene, we still see significant proton conductivity, but for 2 layers of graphene, we don't see any proton transport at all. So the layer dependence of the proton transport can be understood straightforward from the stacking of these crystals. So when you look at how HPN stacks, it stacks in A prime pattern. This means that the atoms of each layer stack directly on top of each other. And this means that the space between these atoms remains open for proton permeation, even for multiple layers. Now, for graphene, what you have is AB stacking. That means that the atom from the next layer sits directly in the center of the previous one. So you block proton currents for 2 layers already. So what we interpreted this is, well, protons are going through the pristine crystal of the material, and therefore they must be piercing the electronic cloud in this crystal. So to understand why this is happening, we did some calculations, our colleagues did, and this is a calculation of the electron cloud density in the crystal. And in this calculation, the darker it looks, the more dense the electron cloud. And you see that HPN, which was the most permeable material, is the most translucent of these 3. It's more translucent than graphene, and MOS2, for which we didn't see any conductivity, has pretty dense electron clouds. Another interesting property of these crystals that is relevant for today is that they turn out to be perfectly selective to protons. So to see this, what we did is we got these membranes that we make, And this time we use them to separate two reservoirs, one high concentration electrolyte and the other low concentration electrolyte. So when you do that, if your membrane is selective to the positive ions, what happens is the negative ions are repelled, the positive ions can go through, and because of this concentration difference, you create a current by diffusion. Now, the interesting thing about the system is that, of course, you can stop this current by applying a voltage. And the voltage necessary to stop it in the limit where the crystal is perfectly selective to ions is given by this very simple relation. Basically, fundamental constants and the log of the concentration. So our IVs look like this. This is for hexanyl boron nitride. This is current density versus voltage. And what we did is on either side, we put a concentration factor of 10 in hydrochloric acid. So this is 0.1 molar and 1 molar, 0.2 and 0.2, 0.3 and 3. And what you see is that the absolute value of the current, of course, increases. But the interesting thing is that the voltage necessary to stop the current is always this perfect selectivity potential, this 58 millivolts per decade. And what this tells you is that the chlorine ions are being blocked in this system and that the crystals are perfectly selective to protons. Now, so far we have always interpreted transport through graphene by saying that protons transfer through the pristine crystal lattice. But it's, of course, it's been proposed pretty much from the first days we published this work, that you could also have proton transport through defects in the crystal. And this was measured with optical experiments, second harmonic generation. And what they did is they covered an oxide, a silicate, with CVD graphene, and they exposed it to potential pH changes, and they monitor the change in the optical signal. And what they said is, well, we do see these defects. These defects are very rare. They happen every 1,000 square microns or so. They're separated by about 30, 40 microns, and we think that proton transport does not happen through the crystal lattice, but instead it happens through these vacancies in the crystal. So this was in 2014. More recently, there was a very interesting paper by the group of Pat Unwin in work, and they did the following experiment. So they got CVD graphene, this layer here, then they put nothing, which is a proton conductor, and then they bonded everything with a platinum electrode. And what is novel about this technique is that they use a very small pipette. This pipette is filled with hydrochloric acid. What they do is this little pipette they approach. What it approaches, it injects protons through the system, and then they get collected by this circuit here. Then they retract, and they approach again a different location. And this allows them to map the proton conductivity of the whole device. And what they found was, again, what was claimed before, that for CVD graphene, they still see these isolated spots of current. These spots occur, again, around every 20, 30 microns or so. And these currents are of the order of nanoamperes. So when we saw this paper, we were very interested. So we decided to contact Pat and told him, well, maybe we're wrong. And indeed, protons do transfer through defects in graphene. But before we do that, why don't you measure one of our samples? So we sent him our samples. Our samples consist of, as we discussed before, a hole in a substrate, typically silicon nitride. And this silicon nitride is covered with a two-dimensional crystal. In this case, it could be graphene or hexanyl boron nitride. And the idea is the same. So this pipette is basically like a conductive AFM, but for ions. And what they do is they approach with this pipette, they inject the protons and collect them in the nothing. So in our samples, the back of these devices, so this is the suspended area, this is the silicon nitride, and underneath everything is covered with this proton conductor polymer. So they approach with this pipette. And what they see is fundamentally different to what they had seen before. So they typically, if you look at this, is typical map of this technique is called SECCM, scanning electrochemical cell microscopy. What they see, this is the boundary of this hole. So this hole is this hole here. And what they see is that this dashed line is the opening in the silicon substrate. So what they see is that the SECCM maps are full of active sites. So what you see here, this brown area here, this is the area in the silicon nitride. And the currents that they see here are tiny, so it's of the order of 50 femtoamperes, which is the limit of the resolution. That is, of course, if you try to inject a proton through silicon nitride, well, you can't. This is a very thick insulator. On the areas where graphene is in contact with naphthalene, proton transmission can occur. And now they see over 100 active sites in these devices. So they perform statistics of both sides. So in areas covered by graphene on silicon nitride, what they see is basically there's no current within the resolution. Whereas for the areas where graphene is in contact with naphthalene and proton transmission can occur, then they see currents of the order of several picoamperes. So what this tells you immediately is that, of course, proton transport does not happen through defects. Or, I mean, it can happen through defects, but they're not necessary for proton permeation. There's way too many active sites for these to be defects. So having said that, we can now go even further. So try to explain why proton transfer. So now we know that defects are not necessary for proton transmission. Now we investigate what else can we see. And these measurements are quite powerful because you can correlate the proton activity of the system with the topography of the devices. So this is AFM of these devices, and this is at the same time the SCCM maps of the proton transfer currents. And what we found is that the proton transport tends to happen around wrinkles. These wrinkles are about 10 nanometers or so in height and 100 nanometers in width, roughly. And you can see that many of these active sites correlate with these wrinkles. Although we also see sometimes current around, away from these wrinkles, and around the rim as well. We can also measure boron nitride. This is hexagonal boron nitride monolayer. This is monolayer, and this area is 4 layers of boron nitride, and we see a dramatic drop of current, so basically no current when you have multiple layers of boron nitride. And we see that, again, you have high activity around wrinkles, but you also have pretty high conductivity in areas away from these wrinkles. So what we did was some statistics of how this looks like. This is the current in the pixels, and this is the number of pixels in each of these, a number of pixels for this. And we see for hexagonal boron nitride, we see a bimodal distribution. You see high current, and this mode here corresponds to the pixels around wrinkles. And these pixels here are away from wrinkles. So what we see is that proton transport is strongly accelerated around the wrinkles. Now, for monolayer graphene, most of these pixels are around areas of wrinkles and the rim, and we also see a little bit of activity away, but difficult to tell. Whereas for 4 layers of boron nitride, the current is 0 within the resolution of the measurement. So to try to understand why this is happening, we realized that wrinkles and areas around the rim, they're strained. And the strain in the system basically stretches the system and makes these electronic clouds sparser, basically. And if you look at the energy barriers for proton transport, what you see is that this strain, which is typically of the order of a few percent, does have a significant impact in the energy barrier of about 10 to 20%. And because proton transport depends exponentially on the energy barrier, then these reductions can be significant, and that is why these wrinkles accelerate proton transport. But more generally, what we think this is saying is that, of course, wrinkles are the biggest of all these features, nanoscale features in these crystals. So graphene, if it was completely flat, it would be thermodynamically unstable. So it's always covered in nanoripples everywhere. And these ripples have been characterized with TM multiple times. So we think that these wrinkles are simply the biggest of these features, and proton transport does happen through nanoscale features in the crystal. So that is the background where we wanted to study how interfacial water behaves in this system. So the idea is, well, we've demonstrated that graphene is an excellent out-of-plane conductor. We've also shown that it is impermeable to ions, so it's a perfectly selective interface for protons. And however, it does have another interesting property, and graphene is an excellent electron conductor in plane. So you can dope graphene with electrons and holes by applying a gate voltage. So what this allows you is to use graphene as a proton permeable electrode. So to use this, what we did is we, again, suspend the graphene on a substrate, drill a hot strip. This is about 10 micron. And we covered it with platinum nanoparticles. This is around 1 to 2 nanometers in width, these particles. And then we connected this graphene electrode in a 3-probe electrochemical setup, have a reference electrode, and your counter electrode. Now, the aim of this measurement is to study water dissociation by characterizing the intrinsic proton transport current of the reaction. So we needed to remove free protons. So what we did is we used alkaline electrolytes to remove free protons. So the idea is in this system, we want to measure proton currents in a system that does not have free protons. So the idea is, of course, you apply a voltage. This generates an interfacial electric field. Generates an interfacial electric field. And you split the water molecule. Hydroxide ions are excluded from the membrane. Protons go through, and you measure these proton currents. So what we did is we characterize the electronic properties of the system. You apply a voltage versus your reference. And with Raman, you can extract the Fermi energy of the system as a function of potential versus AGCL. So for around minus 0.2 volts, what we see is that there's the minimum, which is called the neutrality point. When you apply positive voltage in the system, you start to dope your system with holes. When you apply a negative potential, you dope it with electrons. And the doping can be quite high, pretty high in the 10 to the 12 per square centimeter, almost approaching 10 to the 13, which is very high. Now we measure the proton currents in this system, so the outer plane proton currents. And we measure proton currents versus potential versus AGCL. And we, of course, have the Fermi energy of the system simultaneously. And we find two things. The first thing is that as you increase the pH of the solution, the zero current potential moves to the left. Now, so that is known. It's very well known that the water dissociation reaction, the equilibrium potential, shifts to the left when you increase pH. So that's known. What was surprising was that the slope of these IVs increases dramatically, exponentially, actually. So what this is telling you is that the proton currents increase exponentially as you move to the left. And of course, when you move to the left, you're raising the Fermi energy of the system. So for reference, what we did is we put just a few layers of graphene. A few layers of graphene are proton impermeable. And these devices, what they show is absolutely nothing. They're pretty much dead. And so what this tells you is that the interfacial proton conductivity is essential to observe this effect. So we did this systematically as a function of pH and for multiple devices. And this is what you have. This is Fermi energy at the zero current potential versus pH. Each of these little dots is a single measurement, and this is the statistics for each of them. As you see, as you increase the pH, what happens is that the Fermi energy increases. Simultaneously, we measure proton conductivity, and what we see is that the proton conductivity increases exponentially as you increase the pH. And what we did then is, of course, put 2 and 2 together, where you show this is proton conductivity versus charge carrier density. If you have Fermi energy, you can directly extract charge carrier density. And what this tells you is that the proton conductivity increases exponentially with the charge carrier density in the system. Now, up to here, that's where the experiments finish, because that's all you can measure. But we realized that in an electrochemical interface, what happens is you have a double layer, and you have two sections. You have the stern layer, which is basically a capacitor, and then you have a diffuse layer, which is where the ions sort of finish screening the charges from the electrode. Now, because we're measuring with 1 molar KCl at different pH, the diffuse layer becomes a very small contribution, and you can basically model this basically as a capacitor where the stern layer contains all the potential drop. So what this is telling you is that because in a capacitor the electric field is proportional to charge carrier density, what this tells you is that the proton conductivity increases exponentially with the electric field. So again, that's as far as we can go experimentally, so we need a theory, because it would be nice to know what's the value of this electric field. So we need a theory for this, and because there was an exponential relation, we decided to use the theory of Onsager's-Wien effect. So what this tells you is that if you have a weak electrolyte, this could be a weak acid, or it could be, in this case, water, you expose it to a electric field, this shifts the equilibrium of the reaction, and this produces more ion pairs, which is what we ultimately measure. So we fitted this theory to our data, and what we see is that this slope of charge carrier density versus proton conductivity tells you the dielectric constant of the system, in this case interfacial water. And our data is consistent with anywhere between 4 and 8 roughly, and the best fit is around 6 for the dielectric constant of interfacial water. And with this fitting, you can now extract the interfacial electric field, and this gives you that it's around the order 10 to the 8 volts per meter. So what we think we found, or we have some evidence for, is that there is indeed a strong acceleration of water, this interfacial water dissociation with the electric field. So, of course, if you're splitting water, eventually you will start generating hydrogen and oxygen. So we decided to check this to verify that we're indeed splitting water. And what we did is, in this system, we can measure in situ and in real time the amount of hydrogen generated with a mass spectrometer. So the number of hydrogen molecules generated, we can measure in real time. And we also measure in real time the current. So we can account how many hydrogen molecules are being generated versus the amount of current we measure in the system. And this is what we normally see for this system. This is the hydrogen flux in the spectrometer versus the current density in the cell. And what we see is that indeed we see this relation that 2 electrons give you 1 hydrogen molecule, which is what you expect for this reaction. You can also measure the amount of oxygen being generated. Of course, you split water molecule, you generate hydrogen, but on the opposite electrode here, you're going to generate oxygen molecules. We can also do this with this system, and we find this relation, which is 4 electrons to generate this molecule. So what we find is a 2-to-1 ratio between hydrogen and oxygen. And with that, I would like to leave you with the take-home message that we believe that interfacial water dissociation can be strongly accelerated with interfacial electric field, and that graphene can be used as a proton permeable electrode to provide a different perspective to interfacial water phenomena. And with that, I would like to thank everyone involved, my group, collaborator under GAIM, our collaborators in work for these beautiful SCCM measurements, and our theory collaborators in the Netherlands. No, Belgium. Thank you very much.